Welcome. In this lecture, we shall solve some problems based on shear stresses in beams. Solved problem 14 is stated as follows. A simply supported beam 100 mm wide and 150 mm deep carries a uniformly distributed load over a span of 2 meters. If the permissible stress in bending is 28 megapascals and in shear is 2 megapascals, calculate the maximum load per meter run which can safely be carried. The given data is first written and the cross section along with the beam loading are drawn. The maximum load per meter run, that is the uniformly distributed load, is to be found out. This problem addresses the analysis of beams based on both the shear stress as well as the bending stress. The shear force diagram and the bending moment diagram are first drawn with the respective maximum values below the beam loading diagram. We then estimate the area moment of inertia of the rectangular beam cross section about the centroidal or neutral axis. The maximum bending moment is simplified and expressed as a function of the unknown value of the load per unit run. From the flexure equation, we calculate the value of the uniformly distributed load to be 21 kilonewtons per meter. Let's call this as equation 1. From the shear stress equation, the uniformly distributed load is found to be 20 kilonewtons per meter. Let's call this as equation 2. It is required to select the lower of the two values so that both the equations are satisfied and the permissible stresses are not exceeded. We hence select the safe value of the uniformly distributed load as 20 kilonewtons per meter. Let's move on to another problem. The solved problem 15 is stated as follows. The cross section of a beam is a T section of overall depth 150 millimeters, width of the flange equal to 200 millimeters, thickness of the flange equal to 50 millimeters, and thickness of the web equal to 20 millimeters. Draw the shear stress distribution diagram if it carries a maximum shear force of 70 kilonewtons. The given data is written and the beam cross section is drawn. It is required to calculate the shear stresses at important locations in a beam cross section and plot the same in the form of shear stress distribution diagram. The location of the centroid and hence the neutral axis is first found out from usual principles. It is calculated as 112.5 mm from the bottom layer or 37.5 mm from the top layer. The area moment of inertia about the neutral axis or centroidal axis is then found out with a value of 1.3125 times 10 to the power of 7 in millimeter to the power of 4 units. Now, from the general shear stress formula, the shear stress at the neutral axis is found out to be 3.75 megapascals. The shear stress in the layer corresponding to the bottom of the flange for a width of 200 millimeters is found out to be 3.33 megapascals. For the reduced width of 20 millimeters, the shear stress at the bottom of the flange is found out to be 33.33 megapascals, which is the maximum shear stress. As discussed in theory, the shear stress for the topmost and bottommost layers of the section are both zero. We now arrive at the final solved problem of the chapter. The solved problem 16 is stated as follows. A cantilever beam of I section with width 150 millimeters and overall depth 300 millimeters has the thickness of both the flange and the web as 30 millimeters. It carries a certain uniformly distributed load over the entire length. Find the length of the beam if the maximum bending stress is 4 times the maximum shear stress. This problem again addresses the combined situation wherein both the bending stress and the shear stress are present. Let's draw a schematic diagram of a cantilever beam of length L meters loaded by a uniformly distributed load, say W kilonewtons per meter over the entire length. From the theory covered in the chapter 2, that is shear force and bending moment in beams, the maximum shear force is found to be W times L times 10 to the power of 3 newtons. The maximum bending moment is found to be W over 2 times L square times 10 to the power of 6 in Newton millimeter units. Now we draw the cross section of the beam as per the given data and estimate the area moment of inertia about the neutral axis or centroidal axis to be 1.9926 times 10 to the power of 8 in millimeter to the power of 4 units. From the flexure equation, we get the value of W times L square to be equal to 2.6568 times the permissible bending stress. Let's number this equation as 1. Also, we have the shear stress formula simplifying to W times L equals 7.259016 times the permissible shear stress. Let's denote this as equation 2. Inserting equation 2 in 1 and using the given relation between the permissible stresses, we simplify it further and get the length of the beam as 1.464 meters. We hereby complete the solved problems based on shear stresses in beams. In the next lecture, we shall conclude the chapter by looking into some practice problems.